Okay, today we're going to continue with section 8.4. So we are doing kind of stepping away from the sequences and series, and this time looking at something called the binomial theorem. Now, the binomial theorem is something that we should have been familiar with from last year. So remember what a binomial is. We know that it's a polynomial that has two terms. And in this section, we're going to study a formula that provides a quick method of raising a binomial to a power. So here's an example of a binomial, x plus y. And we would have to use the expansion of that binomial if we have something like x plus y to the nth power. Well, it turns out that when we have x plus y to raised to some value n, that each of the terms has three different components to it. The first part of each component is this I'm going to call it NCR of each term. Okay. And so we're going to do the combinations, where this coefficient here is how many different combinations can exist if there are n terms and you're combining 0. This is n terms and we're combining 1. N terms and we're picking groups of 2. And C3 would be n terms and we're picking groups of 3. Okay. And that is given by this formula, n factorial over n minus r factorial times r factorial. And we can look at how we'd find that in a little bit. But that's the first part of each coefficient, or each term, I should say. The next part is we're going to start with the first term that is in the binomial, and we're going to raise that term to the nth power. And then we're going to decrease the exponent each time. So x to the n minus 1, x to the n minus 2, x to the n minus 3, etc. And then we're going to go all the way down to x to the first, x to the 0 power. Now we can't forget about the second term in the binomial, that y. That y is going to start at 0 to the 0 power and then slowly go up. Move up 1 each time. Y to the first, y to the second, y to the third, y to the fourth, and then y to the n minus 1 and y to the n. Okay, so that value that I've highlighted in pink there, again, is the number of combinations that exist when you have n items and you are combining r of them. You're putting r of them into a group. But there's, of course, an easy way that we can do this in the calculator. In the graphing calculator, if I wanted to find what, for example, NCR was, so if I wanted to say, let's say I wanted to find what 8C3 was. Okay. If I wanted to find what 8C3 was, I would type the number 8. Then I would go to Math, arrow over to PRB or prob. I'm going too far. And then you're going to go number 3, which is NCR. And then you pick the other value. And then you press enter. And that would give you the value of NCR. If you have the newer operating system, you can also hit the alpha key and then go to Window. And then it does exist under number 8. In that case, then both little subscripts pop up, and then you have to say that one is going to be 8, and then you have to arrow to the next one and tell it that that's going to be 3. And you get 56, okay? Another way that we can sometimes see this is if we have this notation, this symbol n over r, but no fraction that's in a set of parentheses, is often used in place of NCR to denote binomial coefficients. Okay, so this symbol is the same value as this symbol, essentially. So if I was given what is this notation, 8, 3, we need to remember that that's the same as 8C3, and we found that 8C3 is 56. Okay, so those are some of the computations you have to make for combinations. So let me give you kind of the way that I organize my work when I use the binomial theorem to expand and simplify the expression. One thing that we can make sure that we look at is something called Pascal's triangle. It won't be provided on the quiz or test, but it's a really cool way that we end up getting these different NCR values. Okay, and the important thing about using Pascal's triangle is that we always have to start our counting at 0. A lot of times we look at the top and we're like, oh, here's row 1. But with Pascal's triangle, we have to remember that this would be row 0. The next row would be row 1. The next row would be row 2. The next row would be row 3. So you have to start counting at 0. Now the nice thing about that is that now, do you see the number 2 is in row 2? 3 appears in row 3, so that's kind of fun. Okay. And then the other thing about it is that in addition to starting counting the rows with 0, we also would start counting the columns with 0. So if I'm looking at these two, like this would be column 0, that would be column 1. Okay. So, and I guess we look at these more as like the diagonals. So like this is diagonal 0. This is diagonal 1. This is diagonal 2. Okay. So it always goes NCR. I'll just make a little note of that here. That the NCR can be gotten from Pascal's triangle by remembering that N is the row and R is the diagonal when we start at 0. So again, if I wanted this 8C3, what I could do for Pascal's triangle is I could go to the 8th row, 0, 1, 2, 3, 4, 5, 6, 7, 8. And then I want to go to the 3rd diagonal. So this is the 0 diagonal, 1, 2, 3. And notice that that gave us that 56. But we had to start counting at 0 in order to get there. Okay. And then again, the way that Pascal's triangle was set up is that we have 1 on all the outside diagonals. And the way that it's created is by adding the two different outside pieces to get what the inner piece is. So 1 plus 1 gave this 2. 1 plus 2 gave this 3. 2 plus 1 gave this 3. And then again, we have the 1s on the outside. So then we would start with an outside 1. 1 and 3 gives me 4. 3 and 3 gives me 6. 3 and 1 gives me 4. And then I bring this down. This is a 1. A Again, 1 on the side. Then I have 1 plus 4, which is 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. And then we just have that 1. So that's how you can create that Pascal's triangle, by kind of adding the ones that are around it to get to the next piece below it. So we can use these things to expand and simplify the expression, right? We're going to start with a plus 2 to the 4th power. Now, when I think about that, I'm going to look at each of these different pieces, and each term is going to have one of these pieces, okay? So the first thing that I would do, because our n is 4, is that I'm going to have 4c0 as that coefficient. Then I need to take the first term, which is a, and raise it to the given power, the 4th power. And then I need to take the second term, b, and I'm going to raise that to the 0th power. And that's how we're going to set up each of those terms. And so sometimes, you know, you can do each term separate. Sometimes people like to work their way down and say, okay, what are all the different combinations going to be? Well, the first one involves 4c0. Then we'd involve 4c1, 4c2, 4c3, and 4c4. Next, we would have a to the 4th, and we're going to drop that power each time. So a cubed, a squared, a to the 1st, and then a to the 0. For the second term, I start with it to the 0 power, and then I increase the exponent each time. So 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th. And I deliberately put those, what the first term was and what the second term was, in parentheses, so that, like, deliberately for some of the other problems that we have going forward. Okay? All right, so then the next thing we can do is evaluate each of those different pieces. So here I would take 4c0, and so you're going to go 1, 2, 3, 0, 1, 2, 3, 4. And so that's 4c0. That's going to be 1. Now 4c1, 0, 1, 2, 3, 4, 1. And so that gives me 4. Now 4c2. You can see that you can use Pascal's triangle to work your way across. So we're going to have all of those different pieces as coefficients. If you can't remember Pascal's triangle, you can always, in the calculator, find 4c0, 4c1, 4c2, etc. But knowing to use Pascal's triangle ends up being really helpful. Okay. Now I'm just going to think about these a's to the different powers. This isn't very exciting. This is just a to the 4th, a cubed, a squared, a to the 1st, and a to the 0, which is just a. And now I can multiply 2 to each of these powers. 2 to the 0 is 1, 2 to the 1st is 2, 2 squared is 4, 2 cubed is 8. 2 to the 4th is 16. And now that you have what to multiply, we are going to multiply. We're going to take 1 times a to the 4th times 1. Well, that just gives me 1 a to the 4th, or just a to the 4th, okay? 4 times a 4 times a cubed times 2 would be best written as 8 a cubed. 6 times a squared times 4 is best written as 24 a squared. Next, we can see this would be 32a, and then 16. And so now what we've done is, using the binomial theorem, we have found all of the different terms that would exist when we take a plus 2 to the 4th power. So that would give me a to the 4th plus 8a cubed plus 24a squared plus 32a plus 16. And since in here we're getting polynomials, we don't want to just keep it in this column form. We want to make sure that we write it out. Okay? So that's how we can expand a binomial. Otherwise, we would have had to multiply a plus 2 times a plus 2 times a plus 2 times a plus 2. Do a lot of distributing that might not be worth our while. And I know these numbers weren't bad, so let's kind of take it up a notch and look at what we can do for number 2. In number 2, we have the quantity 5x minus 2y to the 5th. So still a binomial raised to the 5th. Well, because it's to the 5th power, that means that each of the starting quotients is going to be 5c, and then we're going to start with 0 and go on. So we would have 5c0, 5c1, 5c2, 5c3, 5c4, 5c5. Okay. Now we take the first term in the binomial, which is 5x, and we start by raising that to the 5th power, since that's n. And then we'll decrease the exponent. So we have 5x to the 4th, 5x to the 3rd, 5x squared, 5x to the 1st, and 5x to the 0. Now we do the same thing with the next term, and I want you to think about the next term as negative 2y. When you do that, the signs will just pop up naturally, and you'll see what I mean in a little bit. For the negative 2y, we're going to start by raising it to the 0, and then we increase each time. So negative 2y to the 0, negative 2y to the 1st, negative 2y to the 2nd, negative 2y to the 3rd, negative 2y to the 4th, negative 2y to the 5th. Okay? So these are the different things that we'll want to make sure that we can evaluate. It's helpful here not to speed race through these questions. Take it one step at a time. If we're looking at the coefficients here, 5c0 through 5c5, I could look in Pascal's triangle, row 0, 1, 2, 3, 4, 5, and then I should use for 5c0 is 1, 5c1, 5c2, 5c3, 5c4, 5c5. So the nice thing about when we're doing a full binomial expansion is that once you're confident in the row that you're going to use, you can just copy that row from Pascal's triangle to get to those first coefficients. Okay. Now I'm going to take 5x to the fifth. This is not 5 times x to the fifth. I need to raise 5 to the fifth and x to the fifth because this is a multiplication. If you don't know what 5 to the fifth is, that's fine. You can use that in your calculator. We can see that 5 to the fifth is 3125. So that's going to be 3125 and then times x to the fifth. Now I need 5x, both of those factors raised to the fourth. 5 to the fourth is 625, and then we'd have x to the fourth. 5 cubed is 125, and then we have x cubed. 5 squared is 25, and then I have x squared. Then this is just going to be 5x, and 5x to the 0 is again 1. Now let's raise my negative 2y's to the different powers. Negative 2y to the 0 is 1. Now I'm going to raise negative 2y to the first power. That's just going to be negative 2y. Negative 2y cubed, just kidding, yeah, negative 2y squared. I need to square negative 2, which makes it a positive 4, and then y squared. Next, I'm going to cube negative 2. That's actually negative 8, and then we have y cubed. I'm going to raise negative 2 to the fourth. That's a positive 16, y to the fourth. And then I have negative 2 to the fifth, so that's a negative 32, and then we have y to the fifth. Now notice that in this step, when we write it out, all of these things are being multiplied together. So when we want to simplify each of the terms that will go in our final polynomial, we want all the numbers to come before the variables. So here I can multiply 1 times 3125 times 1 to get me 3,125. And then I have x to the fifth, and I don't have anything else. In the next term, I want to multiply all of the numerical pieces together. Because these are factors, we can multiply them together and change the order. So I'm going to multiply 5 times 625 times negative 2. And if you take that, 5 times 625 times negative 2, you get negative 6,250. So that's my numerical coefficient. And then we have x to the fourth and y. Notice that the negative with the negative 2 ends up as a negative coefficient for that entire term. Then I would take 10 times 125 times 4, and that ends up giving me 5,000. And then I have x cubed, y squared. Now 10 times 25 times negative 8, that'll give me negative 2,000 x squared, y cubed. 5 times 5 times 16 would be 400. And then we have x and y to the fourth. And 1 times negative 32 is negative 32, y to the fifth. So when we use the whole term naturally, like I didn't just use 2y, I used negative 2y, notice that the terms end up alternating naturally because I used, I used the exponents on those negative powers that turned them positive. Notice that there aren't any numerical values between x to the fourth and y. Okay, like in this question here, I wouldn't want to put 1,250x cubed times 4y squared. Nope, we combine all the numbers together. So let's write that as a polynomial. 3,125x to the fifth minus 6,250x to the fourth y. That was positive, so plus 5,000x cubed y squared. This is negative, so minus 2,000x squared y cubed. Positive, so plus 400xy to the fourth. Negative minus 32y to the fifth. And that's our little shortcut there. And you might be thinking like, this doesn't seem like any like a time saver at all. You guys, then I want you to take 5x minus 2y, and I want you to multiply it out 5 times. And then you're going to have to distribute, combine like terms, distribute some more, combine like terms. Be careful of your signs. There's a lot of room for error. So the Pascal's triangle is just a really nice thing to use to try to help that. And this pattern is, okay? And again, I'm just going to remind one more time that we always start counting at 0. Okay? Let's do another one of these that's going to maybe look a little bit different, but it's going to be familiar. All right, so you'll see that in number 3, this is dealing with I. Yes, I, the imaginary number. And so when we're doing these, you can see that we're like, if you look at what we just did, we're going to be taking this I and raising it to several powers. And remember that there's some special qualities about the powers of I. When you have I to the first, that's just I, right? Then if you have I squared, do you remember what that represented? I squared was negative 1. Okay. Then if you look at I cubed, that ended up being negative I. And then if you had I to the fourth, that ended up being positive 1. And then what happens is that repeats. So then I to the fifth would be I to the sixth would be negative 1, I to the seventh would be negative I to the eighth would be 1, and that keeps going like that. So we'll use that, okay? And another way, instead of having the large columns, what we could do is we could have a slot for every term. And one of the things that you might have noticed in the last example is that when our power was to the fourth power, we had 1, 2, 3, 4, 5 terms. When it was to the fifth power, we had 1, 2, 3, 4, 5, 6 terms. So there's always one more term than the value of n. So if this is 2 plus I to the sixth, that means we're going to want 7 terms. So one thing that we could do instead is we could write 7 little lines oops, maybe I made some too big, my bad. But 7 little lines that are going to represent what each term is. And on each of those 7 lines, we can put the different pieces. So remember, the first piece of each term is going to be n, which is 6. We're going to start with 6C0, okay? And then 6C1, then 6C2, etc., okay? And so if you want, we could think about what that would be with Pascal's triangle. We could bust that out if we wanted. And so we could go to row 0, 1, 2, 3, 4, 5, 6. And so the coefficients that we're going to need are 1, 6, 15, 20, 15, 6, and 1. So once you get used to that, maybe we don't write the 630 or 6C0. Maybe I'm just going to write this as 1. And then I'll have the other pieces, 6, 15, 20, 15, 6, and 1. Okay. Now we take that first term of the binomial, 2, and I want to raise 2 to the 6th, to the 5th, to the 4th, to the 3rd, to the 2nd, to the 1st, to the 0. Excuse me. And now I'm going to take I and raise it to the 0 and then work my way up. I to the 1st, I to the 2nd, I to the 3rd, I to the 4th, I to the 5th, I to the 6th. Sorry. Okay. And so now we're still going to have these 7 terms at the end, but we need to kind of multiply out what these are going to mean to us. Okay. So if I look at what these mean here, I have 1 times 2 to the 6th. 2 to the 6th is 64. And then I to the 0, anything to the 0 is 1. Right? Next term, I have 6 times 2 to the 5th. So that's 32 times I to the 1st, so times 1. Then I have 15 times 2 to the 4th, which is 8, and then times I squared. Now what is I squared? We said that we knew that I squared was -1. So I'm going to multiply that by -1. Now I have 20 times 2 cubed, which is 8, and now times I cubed. Well, I cubed is the same as -I. So then 15 times 2 squared, which is 4, times I to the 4th, which is 1. Now I have 6 times 2 to the 1st, which is 2, times I to the 5th. Since we're out here, that means that I to the 5th is the same as I. And here I have 1. 2 to the 0 is 1. And I to the 6th would be -1. So again, those powers of I cycle. 1, -1, -I, +1. Okay. And then we're ready for our next pieces, okay? So then we have, what is this? 1 times 64 plus 1. Well, that ends up giving 64. 6 times 32 times I, well, that would give me 192I. 15 times 8 times negative 1 gives me negative 240. 20 times 8 times negative I is negative 160 I. 15 times 4 times 1 is 60. And 6 times 2 times I is 12I. And 1 times 1 times negative 1 is negative 1. Now, before, if it was positive, what we did is we put symbols like, all right, so this is positive, negative, negative. This doesn't have a sign, so this is positive, and then we said that we called it a day. But do you guys notice that we're not done with this one? Because if it deals with imaginary numbers, we want to write things in standard form. And to have standard form, what that means is that we're going to combine all of our like terms together. Do you see that I can combine 64 with negative 240 and with positive 60 and with negative 1? Now I can add those together. 64 minus 240 plus 60, oops, and then again minus 1. So that gives me negative 117. So combining all the real parts together, I get negative 117. And now I can put the imaginary parts together. So I have 192 minus 160 plus 12. Notice I don't even put the I in because those are just coefficients of I. And then I have 44I. And that's going to be what a complex number in standard form would look like. So we'll also be dealing with the pieces for the I's as well, okay? So this is about if we're taking binomial and expanding everything. Sometimes, though, what we're going to want to do is it asks us for a specific term, and we wouldn't want to write out everything in the binomial expansion. We would just want to write out the specific term and decide what that's going to be. And so instead of writing out the entire expansion, you can use the fact that from the binomial theorem that the r plus 1th term is given by NCR and then x to the n minus r and then y to the r. The reason that we're talking about the r plus 1th term is that, remember, we start at 0. So since we start at 0, if I wanted the first term, or I don't know, if I wanted the 4th term, I'm not going to find NC4. I would need to find NC3 for that, okay? Because, again, it's the r plus 1th term. So just be careful with this idea. We'll practice together. Be careful with what your r is. I'll try to show you how to do that. So this says to find the indicated term of each binomial expansion. And it says it wants us to find the 4th term of 3x minus 2y raised to the 9th power. So this 4th term means that that is the r plus 1 term. So r plus 1 equals 4, which means that your r is going to equal 3. And that's what we're going to use in this formula. Okay? So each term is still going to have the same pieces. First is the coefficient. So we're going to have 9 9c, and then we use r, 3. So 9c3 would give me that fourth term. Because remember, if we started at 0, we would have 0, 1, 2, 3. So that's why to get to the fourth term, we would want to use 9c3. Now we would take 3x, and now we're going to take n minus r. So again, our n is 9. We're going to take 9 minus 3 to give me 6. And then we're going to take the next term in the binomial, negative 2, and then that just gets raised to the r power, to the third power. Okay. So notice that these exponents, 6 and 3, should add up to that exponent 9 that's here. Okay. And now that you have that, now we just evaluate like we did each term in the past. Here, if you're just evaluating 9c3, maybe you don't want to make all of Pascal's triangle. Maybe here you want to say, all right, I'm going to hit 9, math, PRB, go to combination 3. And I see that 9c3 is 84. Next, I have 3x to the 6th, which means I need to take 3 to the 6th power, which is 729, and then x to the 6th power. Now I have negative 2 to the 3rd power, which would be negative 8, and then y cubed. And again, to get that final answer, I would multiply these numbers together, 84 times 729 times negative 8. And I get negative 489,888. And then I have x to the 6th, y cubed. Okay. You wouldn't want to write out the whole expansion just to get that one term. It's kind of a little shortcut. Let's use that again for number 5. It wants the 6th term of 2x minus 3a, all raised to the 12th power. Okay. So since we're dealing with the 6th term, that means that r plus 1 equals 6. So the r value we're going to work with is 5. So my value here is 12. So I'm going to start with 12c5. Next, I have 2x to the 12 minus 5, so to the 7th. And then I have negative 3a raised to the 5th. And then I can evaluate each of these. So again, if in the calculator you evaluate 12c5, we get 792. 2 to the 7th is 128, and then x to the 7th times. Negative 3 to the 5th is negative 243, and then we have a to the 5th. And then we would just need to multiply these pieces together. So I can multiply the 792, 128, and negative 243 together. And if you guys trust me, that's negative 24,634,368. And then we have our variables, x to the 7th, a to the 5th. There you go. Okay. All right, so those are some questions that you could be asked in a quiz test situation. You can practice on the homework from the text. Now this says to find the coefficient of the given term. Oh, this should just say find the coefficient A of the given term in the expansion of the binomial. And they give you the quantity 4x minus y to the 10th. And they want you to find the term that's going to look like this, ax squared y to the 8th. And so we need to think about setting what that is going to be up. One of the things that we notice from here is that the y, like the exponent of y, told us what r is. So remember that because since we have y to the 8th, what that is telling us is that our r is going to equal 8. And then we can use the same tactics up here. So I would need the, we want the term that ends up with a factor of y to the 8th in it. So I'm going to start here, and that's going to be 10c8. And then I have 4x raised to the 10 minus 8, so raised to the 2nd. And then I have negative y raised to the 8th. And then I evaluate each one of these. So 10c8 is 45. 4x squared would be 16x squared. And negative y to the 8th would be the opposite. Oh, so I'm doing negative y to the 8th, so I also have to raise the negative. And so that means I'm going to end up with positive y to the 8th there. Because again, I'm taking negative 1 to the 8th, which is positive, and then y to the 8th. Okay. And so then I can combine these together, and I'm going to take 45 times 16, which is 720. And then I have x squared. And I know I wrote plus, but that's just because I accidentally wrote a negative. This is really a factor of a positive y to the 8th. And so look, we compare with what we have here. We have something x squared y to the 8th. So what does that mean about a? That a is 720. Let's do one more like this. We have number 7, where we have 2x plus 3y to the 7th. And the term that we want is that a squared, something x squared y to the 5th. So I look at that last term. And since we have y to the 5th, that means that r we're going to think about as 5. So we'd set up 7c5, 2x to the 7 minus 5, which is 2. And then we have 3y to the 5th. Then we can evaluate each of these. A lot of times I will just get people that tell me that my answer is 21 because they think about this 7c5 as the coefficient. But let's keep with the problem and we'll see why that isn't the case. Next, I have 2x squared, which would be 4x squared. And then here I would have 243 y to the 5th. And so if I multiply 21 times 4 times 243, I get 20,412. And then I have x squared, y to the 5th. And I want that whole coefficient of x squared y to the 5th. And that means that that would be 20,412. Okay, so look at what the question's asking. Example 8. This one seems a little random, but we're planting some seeds for upcoming chapter 11. It says, expand the binomial in the difference quotient and simplify. Okay? And what they give us is the difference quotient is f of x plus h minus f of x over h. Okay? And so they tell us here that our rule for f of x is going to be x to the 4th. So what that means is that if I want f of x plus h, f of x plus h means that I'm going to have x plus h to the fourth. Okay. So what it wants for our difference quotient then is it wants us to take x minus 4, just kidding, x plus h to the fourth, because that would be our f of x plus h, minus f of x, which is x to the fourth, over h. And it wants us to expand on that. Okay? Well, what we can do is we could use the binomial theorem to help us out with this. We can say, all right, let's give that a whirl. Use the binomial theorem on x plus h to the fourth. We know that we would have to have, I'll try to kind of condense it down. We'd have to have 4c0, which is 1, 4c1, which is 4, 4c2, which is 6, 4c3, which is 4, 4c4, which is 1. Okay. Then I would want to take x and raise it to the fourth, to the third, to the second, to the first, to the 0. And then I have h, and I raise that to the 0, to the first, to the second, to the third, and to the fourth. So what happens to each of these terms? We know that this is 1. H to the 0 is 1, times x to the fourth is going to be x to the fourth. We have 4 times x cubed times h. And you could write it like that, but I feel like h is usually supposed to represent an unknown number. So I like writing the x at the end. And so here I have 6 times h squared, x squared, 4 times h cubed, x, and then 1 times h to the fourth. So now what we can do is put that into this difference quotient. So what is x plus h to the fourth? Well, we just saw that x plus h to the fourth was going to be x to the fourth plus 4h x cubed plus 6h squared x squared plus 4h cubed x plus h to the fourth. Okay, so that's what we have here, x plus h to the fourth. Now we need to subtract x to the fourth, which is the value of f of x, and now we're going to put that over h. Now, my friends, let's simplify. Are there any terms we can combine in the numerator? Well, these x to the fourths can cancel. And to feed two birds with one feeder, if I look at all of these different terms that are left, do you see that each of these has an h in it? So what if I pull an h out of each of these terms? Then this would just become 4x cubed. That would become 6h x squared. This would become 4h squared x. And then this would just become h cubed. And then I have that all over h. Oh, what do you know? That factor in the numerator cancels from the factor in the denominator. So all I have left is 4x cubed plus 6h x squared plus 4h squared x plus h cubed. Not really much you can do with that. No like terms to combine, nothing that we can factor out of every term. That's going to be what your answer looks like. Okay, so that's a little bit about the binomial expansion. If you have any questions, let me know. Enjoy.